Yeah, thank you very much, Celine, for the introduction, and thank you everyone for being here. So yeah, I am the SR12 in the CAFE project, and I am Meriem Krouma, and I'm doing my PhD in collaboration between ARIA technology and the LSE, Laboratory of Science of Climate and Environment in Paris. And I'm co-supervised by Pascal Yu and Céline Diondris. And today I'm going to present my work about the Ensemble weather forecast using a stochastic weather generator and analogs of the atmospheric circulation. And I want to start with this journal article where authors were discussing the attribution of extreme weather events to climate change. And in this article, they were talking about the attribution of extreme weather events, but also they were highlighting the needs of weather forecast and the updates to weather forecast, especially to mitigate the weather catastrophe. And I would like to say that also the Ensemble weather forecast is important as it helps to have scenarios and to check which the most probabilistic scenario. And in that case, we could optimize the decision for the agriculture sector, for the energy sector, and so for the weather management, as was highlighted by Emmanuel. Yeah, sometimes the weather management agency, they need to know how to adapt and how to balance between urban demands and agriculture demands. And also the Ensemble weather forecast is important for the subseasonal forecast, as it helps to catch the atmospheric chaotic. And here in this video, I'm trying, or what was highlighted by the creator of this video, which is based on ECMWF data, is that they are showing the difference between the weather and the climate from few days to decades and years to climate. And as was explained in the morning by Frédéric Vittard, the subseasonal lead time is the lead time between 2 weeks to 4 weeks and to the seasonal. And as you can see here, the initial conditions from 1 day to years or decades are different, and mainly the sources of predictability for the subseasonal lead time are associated to the atmosphere, also to the ocean conditions and land processes. And recently, and especially with the improvement of the numerical weather prediction models, there have been an improvement in the forecast of different climate variables, as you can see here in this figure, not only for the time for the lead time, but also for the spatial scale. And a lot of improvement have been done, for example, for the temperature, also for the mean sea level pressure. However, there are still some gaps or some, let's say, the forecast of some variables such as the rainfall or the extreme, it's still lower. And for example, for the rainfall, the maximum lead time is below 10 days. And in my work, our scientific challenge was this question: would it be possible to forecast or to reach the subseasonal forecast by using probabilistic and statistical approach? And that's for the European precipitation, and also for one of the sources of the predictability for the subseasonal, the MGO, the Madden Julian Oscillation. So our solution or our forecast approach is based on stochastic weather generator that has been developed by Pascal Yu in 2013. And this stochastic weather generator is based on the analogs of the atmospheric circulation. And this method, this approach has been tested till now to forecast the North Atlantic Oscillation, recently for the precipitation and also for the MGO. And one of the advantages of this technique is that it has a low computing efficiency. I mean, we can run it, we can use this model in sample laptop. So the idea is to use the stochastic weather generator and as inputs to this model, the analogs of the atmospheric circulation to forecast, for example, the precipitation for the subseasonal lead times from 2 to 4 weeks. I will start by explaining what are the analogs of the atmospheric circulation and why we use them. To answer the first question, what is an analog? So by definition, an analog of the atmospheric circulation, for example, for a day G, we will try to look to a similar atmospheric circulation configuration. And here, for example, we have the day G and we have two maps of Z500. And the idea is to look to the similar or to the closer map. And I don't know if you agree, but the first one is more close to day G. And we can say that the day D prime, the map and the first map is the analog of the day D. Like it looks very simple like that, but there is a mathematical explanation behind this. And in fact, the day D and the day D prime, they are recurrent state. And to quantify that, we are using, for example, the Euclidean distance to quantify this this similarity or this analogy. Then we go to our forecast. And for example, if for today, we would like to forecast the precipitation for 5 days ahead, I will explain how we proceed. So for today, as I explained it, we will look for analogs for this day. And let's say we have 20 analog. We will keep just 20 analogs for today. And if we say that the analog of today is the 3rd of September, 1994, so what we will do, or what the stochastic weather generator will do, that it will take the atmospheric circulation of this date, and we will look to the precipitation for this day, and we will attribute it to today. And our forecast for 5 days ahead, for the 1st of October 2022, will be the precipitation on the 7th of September 1994. So here I try to keep it simple, but keep in mind that we are doing an ensemble forecast and we are generating trajectories, and it's a bit more complicated in reality. So I will move to results, and I will, as I said, we applied this approach for the European precipitation. So what we did in our first paper that was published in GMD, we did a proof of concept. It means that we checked if with this methodology, we can forecast the European precipitation. And we found that combining the analogs and the stochastic weather generator could help to forecast the precipitation up to 10 days, especially in the winter, and for a local scale. I mean, for cities. Here I'm showing in this figure the forecast scale, and I'm using the CRPSS with respect to persistence and climatology for winter, which is represented by blue, and summer by red, for different cities, Berlin, Toulouse, Madrid, and Orly. And as you can notice, the CRPSS against the persistence or the climatology, it has the higher values for the different station in 5 and 10 days, especially in the winter. That's true, the skill score is still positive even for the summer, but it's still less than in the winter. So what we did next, as I said at the beginning, we want to improve the forecast for the subseasonal lead time. And what we did is that we used information from dynamical models. We used the reforecast from the dynamical models, which contains more information about the ocean and the ice. And we use this information to forecast the precipitation. And we were able to improve the skill scores that I'm showing here till 35 days. So this work gonna be submitted soon. And I invite you, if you are interested, to check my poster it is the poster number 7. And then we, as a second step, we used this approach to forecast the MGO, the Madden Julian Oscillation. And as was explained this morning, the Madden Julian Oscillation is one of the sources of predictability in the subseasonal lead time. And also it influences the precipitation anomalies, especially in the tropics, but also it has impacts in the extratropics. And what we did, we adjusted our model to forecast the MGO, for example, to compute the analogs, and the way we are selecting dates with our stochastic weather generator. And we found that we, and I have to mention for the MGO, we used other scholar skills that are the bivariate correlation and the RMSE. And as you can see here in figure A, with the correlation, I'm presenting the correlation for the different seasons. And as you can see, we were able to forecast the MGO till 40 days. However, our forecast is sensitive to seasons. And we found, especially with the RMSE, we reached the threshold, which is about 1.4 for the RMSE for December, January, February, March, April, and May at 30 days. And we can explain that by the fact that during December, January, February, we have what we call the boreal winter, where the MGO is very active and the intensity of the MGO is higher. And for that, we can say that our approach is underestimating the MGO amplitude. However, we checked the ability of our model to distinguish between events and non-events of the MGO, and we found that the model is still able till 40 days to distinguish between active amplitude of the MGO and inactive amplitude. So this work is in review in our system dynamic journal. And if you are interested, we can discuss later about this work. So as I mentioned in the beginning, I'm doing my PhD also with a company. And in a company, we are interested to use this solution and to adapt it to our customer needs. And mainly, we have some proposal that we are working in, for example, for a wind farm company in Brazil, and also an agriculture agriculture company. They are interested in the forecast of the precipitation for the subseasonal lead time. And also more recently, we have this proposal from shipping routing company where they are interested in especially for the forecast of the wind. So we are working on that. We can see that we can use this solution in to answer some of our customer needs. So to sum up, I can say combining analogs and the stochastic weather generator showed the ability and good skill scores to forecast either precipitation and the MGO. Also, I would like to highlight the importance of the atmospheric circulation to forecast the weather. And I can say also that our approach our model showed its capacity to distinguish between events, either for precipitation, extreme precipitation, and also for the MGO. And I didn't show those results here, but also we compared our skill scores to other forecasts from the ECMWF and from machine learning techniques that was used by my colleagues Riccardo Solini, especially for the MGO, and we confirmed our skill scores, or our forecast skill to forecast the precipitation or the MGO. So yeah, that's all from my side. Thank you very much. And if you have feedbacks, they are welcome.
Thank you very much, Meriem. So we have time now for questions. Hi, Maria. A very interesting talk. And I have a question. When you predict the precipitation, the method you use, from my understanding, is that you use you first to see the atmospheric circulation on that day, and then you find the analogs from the history, and then you, based on the historical recording, to predict the precipitation. But currently, on the climate change, we may meet some precipitation that breaks the recording. And I don't know, do you have some comment on that? And can this method, is there some limitation for this method? Thank you.
Okay, thank you, Sanjay, for the question. It's a super interesting question. And the way you described how I'm doing the forecast, it's correct. Firstly, I'm looking for analogs for each day, and then I'm running the forecast. And for the part of the impact of the climate change on our process, or in our model of the forecast, that's true. Yeah, maybe in the future we will see, I don't know, I could expect that maybe using the analogs, I don't know how it will be, but till now I can say, like, I verified by my own how my methodology is picking analog dates. And I can say that I have an equal distribution between past and the current dates. So that's why I think, yeah, we can still use analogs in the future, and maybe we could adjust it a bit depending on the climate variables. But till now, from my experience, I can say that there is no, like, my analogs, they are from different dates, so which is fair. I don't know if that answers your question.
Yeah, thank you.
Thank you.
Okay, we have, no? What's the question?
Thank you. Perhaps a silly question, you will forgive me. Have you quantified for how many days in a row can you get good analogs? I mean, for example, if you know that a good analog of today is, I don't know, the 10th of October of 10 years ago, then a good analog of tomorrow is the 11th of October, and the good analog of after tomorrow is the 12th of October, and so on. Are you able to quantify if there is a chain of days in which you can find good analogs, and which is the length of this chain, let's say?
Okay. Yeah, thank you, Alvaro. And yeah, I didn't explain that, but I am putting some kind of conditions to pick up my analog dates. First, the analog should be from different year. It should not be in the same year. For example, for today, I will not take any analog from this year. So all the analogs will be from previous years. And the second rule is that the analog should be from, for example, for the precipitation, it should be from the same season. It's not from summer, or if it is in autumn, the analog date will be in autumn. And for the MGO, for example, it should be in the same phase. Like, for sure, like, if we are taking in account, for example, for the precipitation in my first paper, we took in account the persistence. I mean, like, we looked for analogs for a period, not just for one day, like taking in account 3 days in advance and 3 days, because we think that the state will stay for a long time, like the atmospheric circulation. But I cannot answer the other part of how much or how I can get, because I have random analogs from different dates.
You?
Thank you for the talk. My question is quite similar to the first one, and it was related really to the availability of suitable analog in the historical record, especially for extremes. So if you look, for instance, at the heat waves in Canada and Western America last summer, it was so far out, anything we have seen before, that you wouldn't necessarily find a suitable analog. How would you deal with this kind of situation?
Yeah, yeah, you are right. Thank you first for your question. And yeah, that's true. There are some extreme events, and as you have shown in this morning, for example, the example from the last, like in 1964. But that's true. There are kind of extreme events that we cannot easily pick up from the database. And for example, for the Canada heat waves, it was like the return period for this kind of events is for 1,000 years or something like that. And for in my current work, I didn't check that, but I know that colleagues from the LSE, they are working in that, and they use the analogs to check for to look for the Canadian heat waves. And I think they find interesting results because they try to pick up analogs with the last year, 2021, and they deleted this year from the database, and they try to find to simulate, I mean, the heat waves. And I'm not sure about the result, but yeah, maybe you can check. But in my case, I didn't really focus on that. But when I highlight here that the model was able to forecast the extreme events, I mean, we looked to some, I took the threshold for precipitation, and I checked if the model was able to pick up those events from the hintcast.
Yeah, thank you for the talk. Very interesting. Yeah, this is kind of a silly, well, I don't know if it's a silly question, but I mean, by definition, you need some similarity between the events. This is how the methodology works, right? And I was wondering, you need the dynamical situations to have some similarity. I was wondering if there is any particular kind of event that is better forecast with this system than others. For example, blocking is better forecast than, I don't know, persistent. For example, a blocking situation is better forecast than, for example, a ridge-like situation. And also link with that, it's how this work, for example, for summer. I can imagine for winter, it might work better than for summer, but I'm not sure, just asking.
Okay, yeah, thank you for the question. We checked the relation between weather regimes, like as you said, for blocking, I used weather regimes, the European weather regimes with for example, the CRPS, and we took like two classes of the CRPS, best CRPS and worst CRPS, and we tried to link them to weather regimes. And that's true. For example, for Orly and for Berlin, we find that the good forecast was related to the blocking. And like, however, for other cities, it wasn't related. It was related to other weather regimes, and that could be explained by the the weather, for example, in Berlin and in Madrid is different. For the second part of your question, that the forecast for the, you said for the summer, it should be better in the. Yeah, it works. Yeah, actually, it works different from one season to another. Yeah, for the precipitation, yeah, the winter, it works better, but with when we try to improve by using dynamical models, I can say like the model is behaving quietly the same in the winter and December, in the winter and in the summer, and we notice a big improvement, especially for the summer. Yeah. Okay.
Other question?
If there's no other question, I would also like to ask a question. First, thanks, Meriem, for the presentation. I was wondering, you're right now basing yourself solely on atmospheric predictors, like pressure on Z500, I think. Would it help to combine this with for example, the state of the ocean, sea surface temperature, and include this into the predictor space, and then find analogs based on both variables at the same time? Or are there any mathematical limitations in the theory that might lead to a very sparse predictor space where it's very difficult to find similar analogs in this setting?
Yeah, thank you, Niklas, for your question. Actually, I tried to use other fields. Like now, for what I present, for what I have presented, I'm using only atmospheric circulation. But also, I have tried either to combine different fields from the atmospheric circulation, or also to use, for example, the SST, the sea surface temperature. And for that, I tried to compute EOFs by normalizing the fields and to look for analogs for the EOFs. For the point of view of the approach, there is no limit. But for example, when I tried to combine different fields from the atmospheric circulation, I didn't, for the precipitation, I didn't notice any improvement like compared to using just one field. And when I used the SST, I don't know, maybe I didn't know which lead time should I, for example, for the SST, you know, like the process is slow, and maybe we need to take data for monthly data, or even like for more like lead time, I mean, but it didn't work. Maybe I didn't know how to use data, or yeah, but I didn't like find any interesting result.
Thank you.
Thank you. Thank you, Meriem. So I'm sorry, but we don't have more time for questions.
Yeah.
So I would like to thank Meriem.